Okay, let's look now at the internet checksum algorithm. So unlike parity, this one is actually based on adding up the data using some kind of regular addition arithmetic, and then so the transmitter adds it up and puts the added value in, and then the receiver would repeat that calculation and see if that matches, and if it does, then there's not been an error, or it assumes there's not been an error. If it doesn't match, then it will assume that there's been an error, and that it needs to get the ask for the packet to be retransmitted or just to throw it away. So the way it works, if you think about the data as being a bunch of 16-bit integers, so each pair of bytes gets added up at a time, we add them together using ones complement arithmetic, which is a little bit different to normal binary arithmetic, and we'll explain that in a moment. And then at the very end, take the ones complement, so flip every bit in that 16-bit value, and that gives you the checksum. And there's a reason why they flip all of the bits in there, which is that if you do that, and if you calculate a checksum including the checksum in the checksum, it should add up to 0. So it makes it super easy. You don't have to check against some other value. You can actually calculate it and just see if the result is 0 or not, which is often a little bit more efficient for computers to calculate and to implement in hardware as well. So ones complement arithmetic is simply where, to make the negative of a number, you flip every bit in the number. In normal binary arithmetic, you flip all of the bits and then add 1, so that's 2's complement. But for ones complement, you just flip the bits. And then if you're adding numbers using ones complement for this checksum, if you have a carry, so if the top bit ends up flipping when you add the two bits together, we need to add that in, and so that actually gets added back into the result, into the lowest bit. So we count the number of carries that have happened so that we're not blind to that either. So we've a little bit more of a look there at doing this. So if we wanted to add -5 and -3 in ones complement using 4-bit numbers, +5 is 0, 1, 0, 1. So -5, we have to flip all of those bits. So the 1 at the front becomes a 0, the 0 becomes a 1, the 0 becomes a... Sorry, the 0 becomes a 1, the 1 becomes a 0, the 0 becomes a 1, and the 1 becomes a 0. So the 0 has become a 1, the 1 has become a 0, the 0 has become a 1, the 1 has become a 0. Likewise, if we do that for +3 to get -3, we can see we've just flipped the bits. In this case, it's palindromic, but the fact that it's palindromic is completely irrelevant. It's actually about flipping the value of the bits in there. So, for example, if we had 6 and -6, 6 would be 0, 1, 1, 0, and -6 would be 1, 0, 0, 1. So if we add together -5 and -3 in ones complement, we need to add together 1, 0, 1, 0 and 1, 1, 0, 0. If we add those two together, we will get 0, 1, 1, 0. But what we do for calculating the checksum is we add that carry back into the lowest bit. So now the result is 0, 1, 1, 1. Which incidentally actually also makes the ones complement addition work in the natural sense, in that -3 and -5 together should give -8. And if we invert 0, 1, 1, 1, we will get 1, 0, 0, 0, which would be +8. So it actually makes it all work. Okay, and cyclic redundancy checks we will do in the next video.